First of all, I would like to clarify, some of you asked me about the exam. So how the exam will be. More or less, as I told you, you have 1/3 that will be based on your report. So the 1/3 of the evaluation, basically, I think it's going well in general for all the groups. I mean, this is, you won't expect, I mean, bad surprises, I would say, under that point of view. For what concerns the written exam, it will be an exam consisting of normally 8 exercises. Each exercise will contain some calculation, which is similar, very similar to what you saw during the project and the exercises you have. So if you are familiar with them and you feel solidly at ease with that, it should be totally fine. There will be also some theoretical questions. Theoretical question is mostly, we do not want you to know how many terawatt-hour are produced by this technology in Switzerland today. So these are information that we give you in order to help you have some data and understanding. What is important is that you understand the principles, you understand where a technology is used, where it's not, and so on. You're allowed to have some notes. Also here, it's as Professor Maréchal mentioned in the first lecture, it's a one-sided 15 pages. So also here, again, we recognize creativity. So if you really want to put some effort in that, there's a way of putting a lot of material in one sheet. Again, we will not be, the main goal of the exam will be to see if you have the basic knowledge, if you understood. So I think even if you come without any notes, it should be fine. We're not going to ask you some very specific details. Just write down the key formulas that you need in order to do the exercises, I would say, and the rest normally should be okay. We'll also upload the exams on Moodle. So you have the previous exams. I will select only the exercises that are relevant for this year because last year there was also the course from Professor Van Elle and Professor Hausner. So they went much more in detail on some technologies. So these exercises would be out of context in this course this year. So I will try to select some exercises, and what I propose to do is that we have a last lecture on December 17th. The first hour it will be me, and I will open a speak-up system for that. And what I ask you is to write there what are the exam questions that you want to discuss. And I will dedicate that hour mostly to answer these questions, to check together the exercises and so on. Okay? So I will put them a bit in advance so you have time to see it. And a last thing is that the speak-up system and also the assistants and us will be also available in January. But let's say, remember that every one of us, especially also the assistants, have their PhD to do. So the hours in which you should profit of their time is when they are here in class, and not in January at the last minute ask a lot of questions, because they are nice, they will probably answer, but okay, take into account that it's actually not the main thing they have as their job. So, any question about the exam? The idea of this short presentation is to give you a very brief introduction about the model that you have, that you're using in the course. This won't be something that you need to know for the exam. It's mostly to help you, since you're asking questions that are quite relevant, I have to say, about what's behind the scene. So it was our idea to leave it in two-level approach. So we wanted to give you an Excel interface to make it super easy to do the project. So you can satisfy the minimum requirements with that, actually even all the requirements, I would say. But if you want to do more, there is a lot behind the scenes that you can explore. And of course, we appreciate if you do it in the sense that it shows a sort of that you're interested and you get. So the main point, I will very briefly tell you why and what is the energyscope model. Also tell you that there are different versions available and you're getting a somehow simplified one, I would say, for the course. And then to understand what optimization is, I will give you a very, very brief introduction on what an optimization model is, which I hope will be of interest, and anyway, it's something that you need. And then I will just show you, if you have questions on the project, I will just show you what are these mysterious files that you have in the folders on Moodle, so you see a bit what's behind the scene. So, a brief history of why is energyscope. So, energyscope started more or less when I arrived at EPFL as a project, so this is the name, energyscope is the name of the model. Basically, when I arrived, there was still as head of our lab, Professor Favra, a very intimidating and extremely knowledgeable professor. I was a very young PhD student hoping to save the world. So he came to me once and I was already a bit afraid of what would happen. So he told me what was my plan. And as every young PhD student in the first year, I said, I want to save the world. And he told me, yeah, sure. What about starting from Switzerland in the first 6 months and then we see. And in this moment, there was a big debate about the phase out of nuclear. So you have seen this graph various times, so the balance of demand and supply in Switzerland back in 2011, and the strong contribution of nuclear, the Fukushima accident, and the fact of how then to replace the gap created by nuclear power plants, okay? So the first part of the project that we did is we started developing a model in Excel. The model in Excel was called, is what you find still in the online platform energyscope.ch. And here you have to acknowledge that most of the work, especially in this Excel version, and I put all the references up here. So when you don't have anything else to do at night, late at night before going to bed, this is a good read. You fall asleep very easily. And I have to say that most of the work here needs to be acknowledged was done by Victor Codina Girones, our colleague, who focused a lot on energyscope model, collected a huge amount of data, and that's what made it possible also the next development. So at some point we realized, okay, the Excel model is not enough, because you can imagine if you want to do to implement a storage technology in Excel, you have to tell him, okay, if there is this condition, then do this and so on. When you have 70, 80 technologies available, Excel is not able, well, there is some optimization possible in Excel, but it's not the best tool to do this. So we transform Excel, the Excel version, into an optimization model. And that's what I would like to explain you what it is today. So the current version is the one that is available in my thesis up here. It's also available on GitHub. It's an open source code that we made available and which we're currently still working. I have to say that in my thesis, my plan was only to work on uncertainty. So one alternative, if you don't want to read my thesis, is basically summarized by this diagram here that a good friend of mine made. So my goal was only to focus on the impact of uncertainty in energy planning. I ended up having to somehow create a model for it just because I couldn't reuse any of the existing model available in the literature. Why this? Because if you look in the literature here, I wrote down a comparison I did in a paper between existing energy models. Basically, we needed something which was comprehensive enough and so on, so that that was open source, that optimized the investment and operation of the energy system at the same time, that covered heating, mobility, and electricity, not only electricity, and that was fast to solve. And among the models that are available in literature, and there's many of them, we needed to, we didn't find one that was exactly fitting our characteristics, and so we developed a new one. So that's why you have this model that you have there. And what is energyscope? So basically, as you have understood during the project, is an optimization model, and I'll explain you now what it is, which given as input the resources, the technologies, the demand of a given future year. So we are looking at the future year and optimizing that year. Most models, they usually model all the years in transition. We look at the future year, also for computational reasons. So we just want to define the target. And basically, we find the best solution, as you saw in your project, in terms of cost or in terms of emission, subject to the constraints, which are basically, we want demand to be satisfied, we want the technologies to be used by the available amount, we don't want solar to be used at night, and this kind of thing, okay? The output of the model that you have is that if you look in your output files, the F mult is what I call here F, so the size of the technology that you install, the gigawatt of technology that you install, and the F mult T, so the FT here, is the use of the technology that you have over a different months, okay? So the input that you give is resources, demand, and so on. The output is the, if you want, energy strategy, okay? I want just to mention that the model that you're using is a model that looks at Switzerland in a future year. In your case is 2050, and it has a monthly resolution. So it takes into account only the energy balance across the different months. The working version I'm using today in my research is an evolved version that we're publishing right now. It basically takes into account all the hours of the year, and we have typical days, which means that we create clusters over the hours of the year in order to identify typical days, and then we're able to plot nice graphs. But they do not mean anything, but they have a good color combination. So you see that, for example, there are some days in which you can store excess electricity, or you can store excess heat, and then you give it back to the system to couple the demand, okay, to meet the demand. So this is the version that we have. We didn't give it to you because it's not finalized yet, and also instead of just uploading the file and having it solved in basically 1 second, you would have to wait 1 minute or so on, so it would be less user-friendly. But it's the same thing that you have, just with a bit more evolved, many more technologies, and especially storage, and a higher definition in time resolution. Okay, so this will be available on GitHub soon. If you want to play with it in the future, go ahead, and it is there. So your application, the model that you have for Switzerland, what does it have inside? So we told you it is for 2050. We lied. It's for 2035 in reality. So the data we collected, we looked at 2035, 20 years ahead. For simplicity, we just said we assume that the demand will be the same in 2050 for the project because all the energy strategy and let's say fossil-free Switzerland is something that is projecting more for 2050, I would say. But conceptually, as I said, you have Switzerland in 2035, 2050, let's say, with a monthly resolution. And you have, so the model, the original model, which is the one that we originally created, we adapted it to the case of Switzerland. So for example, we did a quite detailed implementation of the storage in the dams. And these are the technologies that we implemented. Okay, so if you look, this is a diagram. All this material is available in my thesis if you're interested. But anyway, we implemented all the main technologies that are available available in the system. For what concerns storage, we're considering only storage in dams and power to gas to power system, as the one I described in the previous lecture. And then you have all the different technologies for electricity, heat production, and mobility. Okay. We validated the model on Switzerland today. So some of you asked what if we could. So of course, if you set that the production of different technologies, the shares of the mobility and so on is equal to today, we did a comparison and we are able to reproduce quite exactly what is happening in Switzerland today. So of course, you could use this kind of model just by setting the coefficients and reproduce the situation of today, and that's what we did to validate it. Okay? So, any general question about this? Yes?
So you're optimizing either cost or emissions, whereas is it also possible to have, like, let's say 50-50 or something?
Yes, so this is a good question. In optimization models, you have different kinds of models. Linear models admit only one objective. So you can only optimize one objective at a time. Of course, this objective can be a weighted sum of different objectives. We do not generally like this approach because the problem is defining the weights. You have different unit measures and so on, so it's not so easy usually to put them together. You could use a CO2 tax to put the emissions inside the objective. This is a smart solution. What you can do normally is what is called Epsilon constrained optimization. So it basically means that if you have two objectives, you can optimize but for one objective, and you can set the other objective to be lower or equal than a value. So you say, you can basically tell the model, I want to find the optimal cost solution with emission being lower than this amount. And you can lower this amount until you eventually, what you'll get is a sort of a Pareto curve, until you eventually get to an infeasible solution because the model says, look, with this constraint you're giving, I'm not able to offer you any solution. Okay? So let me briefly, in like 5-10 minutes, explain you what an optimization model is. My work really lies between energy system and optimization. So I don't know well any of the two fields. What saves me is that I lie in between, and so I have some work to do there. And so in my thesis, I work a lot with optimization models. And optimization is a very wide field, very powerful. I actually, when I studied it during my master's, I did not understand really what was its real application. I learned it during my PhD, I have to say. So optimization is everything you do when you want to minimize or maximize a function at the end of the day. When you're taking, for example, a 3D function and you're doing the partial derivatives of this function, you are optimizing it. In the sense, the simplest optimization you can do is taking an equation, derive it over the variable, and finding the minimum and the maximum, right? So it is, in theory, or analytically, as simple as that. It was born in around 1940 by basically, actually, it was born in production lines. People wanted to find the best way to control a complex batch and production line, and they started to say, okay, we have some variables, so we have some things we don't know and we want to determine. We have some restrictions, so we want, for example, the demand to be met, we need to produce a given amount of product and so on. And we have, so we have variables and restrictions, we have some input data, right? So these are the three things you need: data, restrictions, and variables. And at that point, the problem was very difficult to solve because you have many equivalent solutions that can satisfy the restrictions and can also satisfy the restriction in multiple different ways. The key idea, the smart guy here was George Dantzig, I think in the 1940s, who basically said, why don't we just do this and we add also something, let's say a particular constraint, a particular restriction, which is called the objective, that we want to minimize or to maximize. So now we have a criterion to choose what is the minimum and the maximum, okay? So, very simply, a kind of optimization problem can be read like that. For example, you have a steel production factory and you have to allocate the time between two products. So for example, you have to produce bands and coils. These will give you different profits. They will have different costs to be produced and different times that are available and a maximum capacity. Okay? So this is the kind of problem that we have. Let's try to see, for example, let's see how this problem is mathematically. And this is exactly what you find in the energyscope model. This is just a simplified thing at the end of the day. So what we want to determine is how many bands, so let's call it HB, and how many coils we want to produce in a week. Okay? So what we want to do is to maximize profit. So we have a function which is, so we want to say maximize what? So we maximize the profit. So the bands gives us $25 per, yeah, of course, it's $25 per hour, not ton. So $25 per hour only, of course. So it's $25 to if you produce one band, and 30 if you produce one coil. Okay? So this is your objective, the thing you want to maximize. This is subject to what? It's subject to the fact that you have a maximum amount of coil that you can produce. So the maximum amount of, the maximum amount of bands is, for example, 6,000 tons. The maximum amount of coil is 4,000. Okay? And then you have a restriction on the production time that you have available. So you have 40 hours available in a week. And so, for example, you know that the amount of bands that you can produce divided by the time per hour plus the amount of coils divided by the time to produce it, this is the total number of hours that you have, is lower or equal than 40 hours that you have available in a week. So this is how you get from a problem, a real world problem, to its mathematical formulation. And this problem is super simple in reality. We can even solve it by n. To solve it by n, we can just look how much is the profitability of bands and how much is the profitability of coils. So if you look at it, if you produce bands, so you have that bands give you 25 tons an hour, $25 per ton, and they take 200, and you can produce 200 tons an hour. So the profitability of bands will be 200 times 25, which, if I'm not wrong, is 5,000. And then the profitability of coils will be 140, the time to produce them, times the profit, which is 4,200, okay? So the solution to this problem is pretty simple. We have a linear problem, we try to produce as many bands as we can, and then when we are done with that, if we have enough time, we produce the rest. So if you look at this problem here, it's the only example I make you just so that you have it in the future, is that we can produce 6,000 tons of bands, and then we start producing coil. This is the optimal solution, and you can represent it also graphically. So an optimization problem at the end of the day, it gives you a space. This space gets smaller because you're adding constraints. So these are the constraints that I just wrote there on the blackboard, right? And this is the feasible space of solution. So any solution inside here is a feasible solution to the problem. But you want to find the optimal, so you add the objective function, and when the objective meets the feasible space, then you have a solution. Okay? And this, you can solve this problem that, okay, now this one was super easy, so I solved it by hand, but you can also solve it with a calculation. So for example, I show you here an example. I will upload these files to Moodle. You see that every optimization problem is made of a mod file where you write the equations. So for example, in the mod file, you would write the fact that the objective that you have is the maximum total profit. You have is subject to time and is subject to a given availability of the resources. These data are given in another file, which is, for example, this one. So in here we are just giving the parameters of the cost and availability. And then in this case, but this is specific to Ample, the software we're using, you have a run file, which is the file in which we put together all these things to solve it. So for example, in this case, if we try to solve this problem, let's say, if everything works fine with the connection, the system will tell us that solution, okay? So these problems, of course, normally we cannot solve them by hand, it's complicated. We write it down in code. So this is exactly what you have in the Excel interface and the model that you have online. Actually, I put there some other example. I don't want necessarily to focus too much on them. I will just put them on Moodle. I put you also an example of a particular case, which is when you have also integer variables. So for example, this is another kind of problem that you can solve, far more complex, in which you have a backpack. You have different values or different items of different values you want to put inside. And you have to decide if you want to put or not the decision 0, 1, if you want to put or not a given item in the backpack. And you have a limit on the weight. So you get a formulation like that. You can implement it in your code. And this is what optimization does. Okay? And if you want to get to the general formulation, if you have a mixture between linear variables, as we had before, in this case, and integer binary variables, as you had in this little example of a backpack, then you get to what is called a mixed integer linear programming problem, and that's what you have in energyscope. For example, in your model, you have that the energyscope, you have that the energyscope is the decision variables, for example, in the model that you have, are the size and the use of the installed technologies. The input data are, for example, the demand, the efficiency, the limits to the use of the minimum and maximum technologies. And the constraints are, for example, the energy balance, the mass balance, and all the other characteristics that you want to satisfy in the system. And then you have an objective, which is the queen of the constraints. It is the function that you want to minimize or to maximize. So with that, I basically gave you a very short introduction to what an optimization model is. What I showed here in the whiteboard is basically the same you have in your model. It's just your model is far more complex than that. And what I would ask you now is that do you have any specific question that you would like to understand and see inside the model? Any parameter that you are wondering, I would like to change this parameter, but I'm not able to. I would like to understand where this parameter is written and so on. Is there anything in particular? Because I think some groups, for example, wanted to change the efficiency of technologies. You had a question?
Yeah, for instance, if we manage to make the mobility fleet, the car fleet, completely electrical,
Yeah.
how can we model that?
So for example, what you can do, normally you have various ways. So let's take what I show you. In the last part of the presentation here, I have put a brief description of the key equations in the model, but I prefer to focus on this kind of question because I find them also relevant for your understanding. So this is the file, this folder is the file that you find online in the energyscope, right? So you have the Excel interface, that is the beginner stage, let's say, and you have the advanced stage, which is the mod and .dat files and so on. So if you open these files, you can open them normally with a normal text editor. Let's see a bit what you have inside first. So again, this is the run file. This file you don't need normally to touch it. It is the file in which you have declared what other files you need, and then you call the solve command. And then again, this is all the code that we write in order to write all the output text files, okay? So this one is more our development part, let's say. Then you have two files. One mod file which contains the equations, let's say. One .dat file which contains the data. So for example, in this file, you find the energy demand, okay? Each parameter here, you find a reference to the table in the appendix of my thesis where you find where these data come from and the sources and so on. And every time you add a new technology in your sheet, what happens is that you add a new line to this file. So we isolated the part of the technologies related to this file. You see that here, this is what you get at the beginning of the course. So I commented out the new technologies that you learned in the course. So each time that you are adding a new technology, what happens is that you're adding a new line to this file. Going back to your question, how can we influence public mobility? So for example, public mobility, if we want to touch it, we can go, let's say these are the characteristics of the technologies. So you see that for each technology, we define a minimum and maximum penetration, okay? So for example, this minimum and maximum penetration that you have also in the Excel file are the percentage share that each technology will cover inside a given sector, okay? So in this case, if you go in the mobility sector, what you can do is that if you want all electric mobility, you can put the battery electric vehicle, you put the minimum and maximum to 1, and for all the other technologies, you put the minimum and maximum to 0. This is one of the many ways that you have to, let's say, to modify a parameter. And in reality, I invite you, if you want to try playing around with this model, what you can do, you can, instead of using the Excel files as you've done up to now, you can really take this model, go and change one parameter. For example, even here you can say, let's say now I put all the technologies available, okay? So here I'm enabling all the technologies. Then I can run the model, right? So in this case, so this is something I can do locally because I have the licenses, but it's the same exact thing you do online. It doesn't change. So you see, it solves pretty fast. It finds the optimal solution. If you go in the results folder, you have all a series of output. So for example, you have the install size of each technology. You have the penetration of each technology in a different sector. If you go in the Sankey folder, you have your beautiful Sankey diagram. And the main thing about it is that you can move it around. So you see that you can do a lot of things. The idea is that if you want to play around with it, you can really take the file and let's take, for example, another example could be, I don't know, in this case, if you want to change the share of, for example, if you want to remove nuclear from this system, you saw that there was nuclear in that solution. One thing that you can do is that here, the maximum share of nuclear, actually the maximum amount of nuclear that you allow in Switzerland in this model is 10 gigawatt, okay? If I change simply this value to 0, I can run the model again. the model finds a new solution without nuclear, and if everything works well, it should have displayed it here. You see? So now you have only natural gas in this case, producing the electricity and so on. You have no nuclear anymore. So if you want to play with the model, you can explore a bit more this mod and that file, and you have, in the slides on Moodle, you find all the equations that are behind. So I don't want to enter too much in details on them because it will probably be overwhelming to see just a set of 30, 40 equations right now. But the fact is that the Excel file does not give you the possibility of changing all the parameters in the model. You cannot change, for example, the demand. This is simply because we have not implemented it yet. It would be quite simple. We just, so far, didn't have time. But for example, let's say you want to change the efficiency of a technology. Maybe this is an example that we can also do. Efficiency of a technology is a bit more complicated to do because the efficiency are contained in this big table, which is called layers input and output. So basically, the way to read this table is, for example, that a heat pump, to produce 1 unit of heat, needs 0.25 units of electricity. So the COP of the heat pump, the coefficient of performance, is 4, so 400% efficiency in terms of a first law. If you want to make a more efficient heat pump, you say, no, I want to put the value of the heat pump of EPFL, which has a coefficient of performance of 5. Well, you can change this value here. You can change this value to 0.2, or you have also other ways that if you're interested, I can show you. You can actually, if you don't want to touch this file, you can use some command to change the value directly in the run file before executing the model. So normally you don't want to change this parameter here. What you normally do is to directly change the parameter. There is a command called let that you can use in the run file directly. But these are a bit more advanced things. If you want to make scenarios anyway, you can really change things from here. You can add equations. You can say, I want the equation, I want the share of the GWP to be below a certain number. I want the efficiency of a heat pump to be higher. I want the demand to be lower. So you can try to put the model to extreme values and see what happens. Okay? So this was just to give you an idea. These files are not so mysterious. It's just they are written, it's something we use for research, so we don't have a beautiful user interface for that yet, at least, because what we care about is the fact that the numbers that come out are correct. But if you want to play with these things, just do it. If you don't know how to do it, you can send an email on the speak up, and we will tell you how you can implement the things that you would like to try on your model. Okay? So from my side, I would say I am done with this short introduction. I hope this was useful / interesting to hear. Do you have any questions or things that you would like to discuss about this? Okay, then if in the next lectures and so on you want to discuss something more in detail, you can come to us and check these things. Otherwise, you keep this as a general theoretical introduction and so on.